All right, so now that we have the notion of the basis of the Euclidean vector space and the concept of a dimension, the natural thing is, can we extend it to some of these more general vector spaces? And the answer is definitively yes. Right. So again, just as a reminder, let's reflect quickly where we've been most recently. So so we said that the dimension of Rn is obviously equal to n. And now, just the word dimension should take on a greater meaning. And I'm just going to use B to represent the standard basis. So for Rn, the standard basis would be, and let's write these as columns. So it'll be 1, 0, 0, dot, 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 0. So a bunch of zeros there. And then you'll have 0, 1, dot, 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 all the way down. You have 0, and then dot, dot, dot. And you'll have 0, 0, dot, dot, dot. And then the very last entry there will be your 1. And then these are the vectors that we can denote as E1, E2, dot, 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 En, right? Yeah, so those are the standard basis vectors for Rn. So if we think about now like our matrix space or polynomial space, what does that look like when we talk about basis and dimension? So let's start with basis first. So let's look at our set of matrices M sub n, M by n, right? So M by n matrices. So now, instead of writing it out in words, let's write it down symbolically, right? So remember, it's a set of all matrices that have m rows and n columns. So to do that generally, you would have our A11 and then A12 and then dot dot dot. And since I have n columns, I have to go across the n there and then dot dot dot. Since I have m rows, I have to go down to AM1 and then AM2 and then dot 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 AMN. Yeah, so you have a lot more entries now. And of course, each of the AIJs can be any real number. All right. Now, because matrices and these column vectors are, kind of closely related, we can take a cue from Rn to come up with our standard basis for our matrix space. And all we would do is, so I'm going to try to kind of write this. And remember what a basis represents, right? There is a unique way of representing every element in the vector space as a linear combination of the basis vectors. There's one and only one way to do it. The easiest way to do that in the case of matrices is to split this whole thing. So there are mn entries here. So we're going to need mn, right? M times n basis vectors. And what you would do is you take out A11 and then you would just multiply it by the matrix 1 and then just fill everything else with 0. So again, I'm going to take my general thing here and just kind of illustrate what's going on, right? So you'd have that matrix, right, times your A11. And then you do the same thing. So then you'd have A1, 2, and then just put a 1 in this position, in the 1, 2 position, and then zeros everywhere else. So you'd have a 1 there, and then dot, 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 0, dot, 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 0, dot, 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 0. And you keep going until you get to the very last entry in the last row, last column. So I'm going to put dots there, and then you're going to have AMN, whatever that number is, and you would use it to scale this vector. So zeros all across there, zeros down here, zeros down, and then the very last entry right there would be 1, right? So this matrix, so what I've written down is how I can take this single matrix and write it as a linear combination of these. So the basis now so the standard basis for our matrix space with m rows and n columns would be these specific mn matrices. So I'm just going to write it like this: 0, 0, right? So that's one element in the basis. Here's another element in the basis. And then dot, 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 and here's the last element, right? It's got to be finite. And then 0, and then like that, right? So how many are there? Well, we need one matrix for every entry in the, one basis matrix for every entry that's in our general matrix. So how many are there? Well, it's m times n. So that means the dimension of our matrix space is simply m times n, right? And this is our standard matrix. So it really gets messy with matrices because you have so many entries, and again, we're looking for this kind of standard, unique way of representing all of them as a linear combination. All right, so that's matrices. What about polynomials? What about our Pn? Well, let's see, we've written this down, so it will be a n x to the n, and then plus a n minus 1 times x to the n minus 1, and then plus dot, 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 a1 times x, and then plus your a0, and then your a sub I can be any real number. Well, the easiest way to write this as a linear combination of polynomials, remember, so your basis vectors are going to be the same type of object, but we're choosing a special subset of them to represent all, right? Yeah. It's like the congress of matrices or something like that. So the standard way to do it is to take, let me just highlight it here, and then I'll write it down formally. So you take that polynomial, and then you take that polynomial. So you're taking basically all the powers of x, right? Here we go. And of course, remember, x to the 0 is 1. So I'm going to put a 1 there. And so everything there I have in red will be the standard basis for Pn, right? Because you need to account for all the powers of x, including a power of 0, right? So here's our standard basis for Pn. It's x to the n, x to the n minus 1, dot, 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 x to the first power, and then x to the 0th power, which is 1. And then if we count, remember the way we define dimension, it's the number of elements in any basis, right? Including the standard basis. So in this case, if you count the number of elements here, remember you're counting from 0 now because it's x to the 0, then x to the first power, all the way up to x to the nth power. So your count is actually n plus 1. So the dimension of our polynomial space is n plus 1. All right. Okay, so the last one I'm going to mention, the C, and I'll just take C for continuous. Actually, let me not use the C with the line there. Let me just use C. And let's say continuous over the entire real line. Let me draw a demarcation line between these two things. So the ones above the line, those are examples of examples of finite dimensional vector spaces because they have a finite dimension. And you can write any element in each of these spaces as a finite linear combination of these elements in your basis. For a set of all, if we say all continuous functions, then suddenly it's unlimited. Let me just give you an example. Let's just take something like sinusoids, so sine and cosine. So obviously sine of x is continuous, and also the sine of 2x is continuous, and the sine of 3x is continuous, etc., with no end, right? And each of these are linearly independent of each other. So you can keep listing just your sine functions, and there's no end to it, right? But all of these are continuous. And then you can do the same thing for cosines, like this, like cosine of 2x, cosine of 3x, right? And then, of course, you can throw polynomials in there too. But if we don't limit the degree on the polynomial, if we just say all polynomials, same thing again. You know, you would start at 1 and x. And again, I'm just listing kind of the what you might try to define as a basis, right? And then you got your x squared and you get x cubed. Again, where do you stop? Okay, and that's just three, standard types. What about all your exponential functions? What about like e to the x or e to the 2x and then e to the negative x and so forth? So the point I'm trying to make here is the distinction between the r, the m, and the p is that those are all finite dimensional vector spaces. But things like your C or C1, those are infinite dimensional vector spaces. So they have a basis, it's just not finite, right? So let's write that down just to wrap this up. So Rn and your M and your P, it's actually Pn, right? So in fact, m by n. So these are all finite dimensional vector spaces, right? We like things that are finite, right? They have a finite basis, and that's why we can give us a very specific form or number for their dimension. But C, and again, this is just an example, right? So something like this is an infinite dimensional, I forgot the word space, vector space, right? And therefore, so its dimension is infinite and it doesn't have a finite basis. We can't just list it like this, all right? So just kind of keep that in mind as we go forward and we draw this distinction between finite and infinite vector spaces. Most of what we're going to work with will revolve around the finite dimensional vector spaces. All right, see you in the next video.